Hello, my name is Oliver Warner and welcome to my presentation based on my project into the causal structure of black holes. Over the past 14 weeks I've been studying the structure of black holes and the different ways people have used over the past 250 years or so to visualize what they may actually look like. To begin, however, I will start by briefly visiting a history of the theory of black holes' existence and theories on how they are structured. So most people give credit to Einstein's theory of relativity for first putting people in the mindset of thinking about black holes. However, the first case of someone proposing the existence of them happened over 100 years earlier, in 1783, by John Michell, a teacher at Cambridge. Michell wrote a paper describing a sphere 500 times bigger than the Sun, where no light could escape it due to its own gravity. Following Michell's ideas, Laplace also proposed black holes existed, with the addition that they may appear invisible to us, as the light cannot escape the surface. It took another 120 years or so before black hole theory got a jump start by Einstein's theory of relativity. In 1916, Schwarzschild solved Einstein's field equations to define a black hole. This was called the Schwarzschild solution, which I'll be using later on. Lorentz followed up on Schwarzschild's findings and discovered the solution became singular at certain points, meaning some terms in Einstein's equations became infinite. This caused uncertainty among the theorists, and because of this, many opposed the theory of black holes and their existence altogether. In 1958, the concept of an event horizon was presented by Finkelstein. He called the Schwarzschild surface a perfect unidirectional membrane, meaning causal influences could only cross the surface in one direction. I quite like this description. Soon after, solutions were found for other types of black holes, rotating and electrically charged black holes. These were found by Kerr. And then in the late 1960s, Stephen Hawking showed that singularities in black holes appear generically in all of them. And soon after, he predicted that black holes radiate like a physical body that absorbs all electromagnetic radiation, which is almost the basis of what we believe is correct now. Like, that was where it really kicked off. This is where I'm going to stop talking about the history, but it's clear that we've come a long way in the field to the point where black holes are universally accepted to exist by virtually everyone. In order to form diagrams of the structure of black holes, called Penrose diagrams, we need a new set of coordinates when working in both Minkowski and Schwarzschild spacetime. So we must undergo coordinate transformations, called conformal transformations or conformal compactification. Conformal transformations are defined as a transformation that preserves angles, but not necessarily orientation of the object. The main reason we need these transformations is that before compactification, time and space go off to infinity. But after compactification, these infinities can be thought of as points. A nice non-mathematical way of representing this is these train tracks, where it appears they're going off to infinity in the picture on the left, but if you think of it as a perspective image, it actually is going off to one point in the second image, and I just thought that was a really nice representation of what it actually is. I will explain more later as to what each Penrose diagram is actually showing, but for now I will move on into investigating Minkowski spacetime. So, Minkowski spacetime is a four-dimensional manifold where three of the dimensions are the usual Euclidean dimensions, with time acting as the fourth dimension. Spacetime intervals between two events in Minkowski spacetime are independent of the inertial frame of reference where they were recorded. But the main way Minkowski spacetime is unique from standard four-dimensional Euclidean space is that in Euclidean we have that each individual component will be different due to things like time dilation and length contraction. Whereas in Minkowski, since all events are independent of the inertial frame of reference, all frame of references agree on distance of events in spacetime. One other thing is the Galilean group is also relevant for distinguishing Minkowski spacetime from Euclidean. Galilean group transformations preserve Euclidean distances but only spatially. Time differences are preserved separately. In Minkowski, space and time are interwoven together, so are preserved in the same transformation. To understand black hole structures in Minkowski spacetime, the Penrose diagram must be obtained by completing the coordinate transformations and conformal compactification. I won't go through the calculations since they're straightforward and long-winded, but the line element in A, ds squared equals minus dt squared plus dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared transforms into the other one. I won't read that one out. So we can use these new null coordinates to begin to form the Penrose diagram. So here we have the Minkowski-Penrose diagram. The actual parallelogram, I guess, is a three-dimensional diagram of our universe. The region's boundaries represent the conformal structure of infinity for Minkowski spacetime, which I like to write in terms of P and Q, and I like the notation of scry to make it a lot easier to actually annotate it by hand. But we've got the future null infinity, which is the sort of top right boundary line. We've got the past null infinity, which is the bottom right. Future time-like, which is the point at the top. Space-like infinity, which is the point at... Oh, it's not the point, it's regarded as one point, but it's the three-dimensional ring in the centre. And the past time-like infinity, which is the bottom point. The curves, r equal constant, correspond to histories of the two-sphere, which basically are like, because that's the time-like geodesic, all the different histories of the sphere are presented on that. And ingoing and outgoing radial null geodesics are represented by the straight lines p equals constant and q equals constant, which make up the 45 and minus 45 degree angles of the light cone, which is in pencil in the inside of the diagram. So if we now look at Schwarzschild spacetime, we have that bodies that are isolated in an otherwise empty space with no external influences. The Schwarzschild solution, representing the space outside of the spherical body, can be used to describe systems that cannot be described as well by other systems. For example, the geometry of our solar system. It's very difficult to describe that in a different way other than Schwarzschild. Black holes in Schwarzschild spacetime are categorized by their event horizon, since this is the part that distinguishes the inside of the black hole from the outside. Matter cannot get out into the rest of the universe once inside the event horizon. Once again, we do a conformal transformation to go from the metric at the top to the metric at the bottom. Again, the calculation is pretty straightforward. It's just coordinate transformations and just swapping in and out between coordinates, null coordinates. So we obtain the Kruskal coordinates, which are u and v, and can form a Kruskal diagram that reveals a larger manifold than just the region covered by our original Schwarzschild coordinates. So we've got the surfaces described by an equation of the form uv equals constant, which corresponds to a two-branch hyperbola, which we have on the right. When r equals 2m, we have that uv equals 0, as you can see from the equation above. So u would equal 0 or v would equal 0, and so there are two copies of each surface. But the Schwarzschild coordinates give us region 1 in the diagram, which is the far right region. The metric through r equals 2m cannot actually pass into regions 2, 3 or 4, because you can see when r equals 2m that makes up the two lines on the right hand side. And so the other regions only exist when you compute the maximal extension of Schwarzschild spacetime. The Kruskal coordinates u and v combined with the transformation u prime equals arctan u, v prime equals arctan v gives us the following Penrose diagram, which is a pretty straightforward one. I'm not really a big fan of this one, so I'm going to breeze over this and make it a lot easier for me to understand or for me to explain in this second one here. So it's the same diagram, it's just different notation and a bit easier to understand for me. The right shape is our universe, just with the Minkowski Penrose diagram we had earlier. The left shape would represent a parallel universe. The top triangle is a black hole, the bottom triangle is a white hole. And this is because the upper r equals 2m there is the event horizon of the black hole, so everything that goes in doesn't get back out again. That's where all of the light and things are getting shoved up to, and then it's going to get drawn into the black hole. The lower r equals 2m is the anti-horizon of the white hole, where nothing can actually get in, and so it's the polar opposite of an event horizon, effectively. The upper r equals 0 sort of wiggly line is the space-like singularity. The future null infinity is the scry plus. The past null infinity is the scry minus. That's on both sides with the universe and parallel universe. Where scry plus and scry minus meet is the space-like infinity, which has the label I0. The future time-like infinity has the label I plus, and the past time-like infinity has the label I minus. And that's sort of the whole basis of the Penrose diagram. I mean, once you understand the ins and outs of it, it's alright, but it's a bit... I wish I would have annotated it a bit better, is what I would say to that. So now we're going to move on to a particle falling into a black hole. So if a particle does fall into a black hole, then we know when it crosses over the event horizon, it will speed up as it gets closer to the centre. If we imagine that this particle fell from infinity, then by using the rules of kinetic energy equals potential energy, at some point d we can calculate its speed. So I've got it on the slide here. This would be a very basic calculation. We've got v squared equals 2gmr, where g is 6.67 times 10 to the minus 11. And if we consider an object falling through the event horizon with radius r equals 21 kilometers and mass 1.2, it's just rearranging the equation to get the speed, so it's pretty straightforward. So yeah, we found the speed of an object falling through a black hole. In the second semester, I will greatly elaborate on this by comparing this speed to someone trying to escape the black hole, and consequently how long it will take both objects to reach the centre. Also in the second semester, I will investigate the Kerr model of black holes, which involves rotating uncharged black holes. I will then investigate further and look into charged rotating and charged non-rotating black holes. Lastly, I'll look into Kerr de Sitter and Kerr anti-de Sitter. So yeah, I've really enjoyed this project so far, and I'm looking forward to furthering my investigation in semester 2 on the causal structure of black holes. Thank you for listening, and if there are any questions, let me know.